Welcome back. Let us continue with an extremely important chapter, namely the basics on size distributions. First, we have to briefly recap the concept of equivalent diameters. This concept is based on the comparison of a particle property that can be measured, e.g. the particle volume, with the corresponding property of an ideal sphere. This is best illustrated with an example, namely that of dV. This is the diameter of a sphere with the same volume as the particle. We hence call dV the volume equivalent diameter. As shown here on the right, we consider V as the measured particle property. In our case, it is the volume, and we use this information to compute the diameter dV. Next, we need to have a brief look on another important equivalent diameter. Specifically, this is the D32, which is the diameter of a sphere with the same surface to volume ratio as the particle that we are considering. In practice, this is the so-called Sauter diameter of a single particle. Since surface and volumina are important properties in many applications, you can imagine that the Sauter diameter is highly significant in industrial applications. The calculation of D32 requires the knowledge of two particle properties, the surface area and the volume. As you can see, the D32 is hence related to the surface equivalent diameter ds and the previously discussed volume equivalent diameter dV. As shown on the right, D32 can also be directly calculated from the specific surface area of a single particle. We can now see that equivalent diameters are very helpful. However, we are often interested in average or mean particle information. We will have a brief look on such averages here on this slide. Specifically, this is the Sauter mean diameter, or short SMD, of an ensemble of particles. Since you have already understood the concept behind the Sauter diameter of a single particle, it is easy for you to extend this concept to an ensemble of particles. As you can see in this expression, we simply consider the specific surface area SV based on the total surface area and the total volume of the particle ensemble. Thus, we sum over all the particles twice. In the enumerator, you see the sum over the surface areas, and in the denominator, the sum over the volumina of the particles. If we now rearrange the equation, you see the excitingly simple expression here on the right. Other mean particle diameters can be calculated as well, e.g. the arithmetic mean diameter of an ensemble of particles. However, you will see that this mean is not of special interest. It is rarely used in practice. Unfortunately, this concept of averaging over all particles is not sufficient in practice. We would have to store a relevant equivalent diameter for each and every particle in our granular system in order to compute these mean diameters. This is not possible or useful simply because of the huge number of particles in practice. Also, a single property of a whole particle ensemble is often insufficient to describe its flow behavior. Therefore, we need to have something in between, and this is a statistical description of the particle sizes. We have already touched on this topic when talking about the volumetric and number fraction of coarse or fine particles in a bidispersed system. Let us now go back again to this important detail, which is essential to understand size distributions. Specifically, we start by discussing some basics of size distributions. First, size distributions can be represented in different ways. And the first is the so-called continuous description. Thus, the parameters of an analytical expression define the relative amounts of particles in our ensemble. This principle is illustrated here on the right with the dark blue line. Alternatively, we can use a discrete or class-wise description that is available from experimental data, for example. It is important for you that discrete does not mean in this context that we use a per particle description, but that we introduce size classes. Discrete distributions are represented by tables or histograms in practice, and this is illustrated here on the right with the bars. The next concept we need to understand is that different statistical metrics can be used for the representation of size distributions. The first option, shown here on the top right already, and we have discussed it already, is the representation with a probability density function QR, which is also called a frequency distribution. QR is not a probability, but a probability density, meaning that it does not give the probability of something, but its integral is a probability. You will understand that later when looking at the mathematical expressions. The alternative concept to frequency distributions are so-called cumulative probability functions, QR, often simply called cumulative distributions. This concept is illustrated here on the lower right. Our intuition already tells us that these two curves belong to each other. The first thing to observe is that the highest value of QR, which we call the modal diameter, is the point with the highest slope of the QR curve. Thus, we will see that QR is simply the derivative of capital QR, and consequently capital QR is the integral from 0 of lowercase qr. The other key particle size in a distribution is the x50 diameter, or the median. It denotes the diameter below 50% of the amount of particles are located. It can be easily obtained from the Q50 value on this curve. This is already it. I would like to close this discussion of this slide by noting that distributions are not exclusive for size of particles, but can also be associated for any other particle property as well. Examples include the particle volume or the particle surface area, the moisture content, or the particle color. Researchers even study distributions of two particle properties, e.g. combined particle size and shape distributions. However, understanding these distributions is complex, and we will not touch on this further. We now come to a set of slides that is critical for your understanding of size distributions. We first detail on what is shown exactly in the plots for the cumulative capital QR and the frequency distribution lowercase qr. On the abscissa, This is relatively easy. It is a size metric, very often an equivalent diameter. As these diameters are based on measurable particle properties, the values on the abscissa depend on the measurement technique that is used for experimental data generation. On the ordinate, we have as the first option the capital QR value, which is, and this is now important, the relative amount of the particle population that is smaller than the corresponding value x on the abscissa. We can express this via this equation here on the left. Very important is to know that relative amount can be different things. How we measure the amount of something depends further specification. For example, it can be the number-based amount or a volume-based amount of the particles. On the right, you see the connection to the frequency distribution lowercase qr. Clearly, we have to integrate qr up to the particle size xi we are considering in our cumulative distribution capital QR. The probability density is a bit more challenging to understand. It is best to again stress that it is not a probability but a probability density. This means that its integral over a certain size range, delta x, has the meaning of a probability delta QR. This probability can be interpreted as the chance of finding a particle in the size range delta xi. Using mathematics, we can formulate this by this expression, which states it in an inverse way. If we want to determine the probability density, we have to divide the probability in a class, denoted as delta qri here, by the range of this class delta xi. Writing this for a limiting small value of delta x, we arrive at the important relation here on the bottom right. You can now also understand the equation here at the center right for capital QR, which connects the frequency and the cumulative distribution of the particle size. As you can see, we left open the details of R so far. We will attack this on the next slide.